Alright class, in today's video we're going to do a quick overview of our three kinematic equations as they appear on the AP equation sheet. So again, when we think about when we're deciding to use these equations, the biggest thing is that they only apply to situations in which we have a constant acceleration. So eventually we'll look at scenarios in which acceleration is non-constant. That's where kind of the calculus comes into play. But for right now, we want to make sure there's a constant acceleration. And if we think ahead to our next unit of Newton's laws, that means we have a constant acceleration if there is a constant force that acts on our object. So oftentimes we'll see in the AP exam is that these questions don't appear by themselves as a standalone problem. Oftentimes we'll either have to use Newton's laws and force considerations, or maybe energy considerations to solve for some sort of part A of a problem in finding an object's acceleration or an object's final velocity. And from there, a part B might then be to, let's now apply our kinematic equations to figure out the time something's been traveling for, or how far it travels during that motion. So when we think about our three kinematic equations, again, one thing we'll notice here is that our subscripts of the x's here, right? This is just our default as if we're moving horizontally. If we are ever moving vertically in the y direction, we can just swap those out for y's. Right? The big thing is we know that our position, velocity, and acceleration are all vectors. So the direction in which we're moving in is important. The key thing is that also means if we say have a negative velocity, we want to be plugging in a negative velocity into those variables. So if we look at our first one, we have our initial velocity is equal to, our final velocity is equal to our initial velocity plus our acceleration multiplied by time. Next up we have our final position is equal to our initial position plus our initial velocity multiplied by time plus 1/2 times acceleration multiplied by time squared. Third kinematic equation, we have our final velocity squared equal to our initial velocity squared plus 2 times acceleration multiplied by final position minus initial position. So again, thinking about how we define all of these variables, right, that little subscript 0 means it's going to be an initial quantity. So we've got initial position. If it's just the x, we have our final position. We have our v initial, or v naught, is going to be our initial velocity. Just v is going to be our final velocity. A is going to be our acceleration. And lastly, t is going to be our time. So anytime we go to approach a problem, again, it doesn't matter if it is in kinematics, energy, rotation, these steps we have here are going to be kind of a way where we can start to break down our problem, figure out what exactly the topics are that align with it, help us kind of map out how we're going to approach it. So again, first thing I like to do is just active reading through the problem, right? Underline, highlight, circle, do something to the pieces of information that you think are important. Next up, I always like to do just a short, quick sketch, a little diagram showing the motion that's being described. And then from there, the biggest thing that's going to help us kind of establish these calculations is we want to make sure that we define whatever our coordinate system is. So again, we want to know what direction is positive, what direction is negative. Sometimes this can even be saying we're viewing this motion from either the point of view of maybe like an outside observer sitting on Earth. Maybe we're taking from the point of view of the object itself. Right. Most cases, there is an easier coordinate system that kind of leans itself to us, but however we establish our coordinate system is acceptable our calculations just might be a little bit more complex. We might have to keep better track of our signs of what's positive, what's negative, depending on how we decide that. From there, especially in these kinematics sort of problems, I'm going to create a quick list of our variables. Right? What are some things that we know? What are some things that we don't know? What is it that the question is asking us to solve for? From there, that list of our known and unknown quantities, that's going to help us decide which equation we're going to have to apply to our scenario. And from there, if we are asked to solve for a numerical answer, right, we want some sort of number as our final result, we can then plug in those values into our equation. If we're going to be deriving something, then again, we'll just keep everything in terms of the variables given to us. So when we think about just a quick example here, right, we've got the sprinter doing a relay. They begin the run, and they grab the baton, and they begin kind of what we call their motion of having the baton with a speed of 2.1 meters per second. They're going to have our sprinter accelerate at a rate of 0.25 meters per second squared. We want to know how far do they go once they reach the speed of 6.4 meters per second. So again, right now, key things that are sticking out to me is that we start our leg with a speed of 2.1. We accelerate at a rate of 0.25 meters per second. Ultimately, we're trying to figure out how far we go once we reach a final speed of 6.4 meters per second squared. So again, what this looks like is we've got our person. They start off with an initial velocity of 2.1 meters per second. And we know that they're going to end up with a velocity of 6.4 meters per second. Now, as far as my coordinate system goes, I'm going to look at the sprinter as kind of like an outside observer standing on Earth. And ultimately, our job is to figure out what is this distance the person travels. So I'm going to go ahead and say I'll call their starting position an x-coordinate of 0. That way, wherever they end up, that final position is going to tell us the distance they've traveled. So from here, when we think about our quantities, right, we say our initial starting position, we're just going to define that as 0. This will often be a very kind of common practice we'll do. Our final position, that's going to be unknown. That's what we're trying to solve for. Our initial velocity set is 2.1 meters per second. Our final velocity is going to be 6.4 meters per second. And our acceleration was given to us as 0.25 meters per second squared. So one thing we'll notice as we decide which of our kinematic equations to choose, we'll notice that we don't have any information about time. So if I go back up to our 3 equations, I really can't use any of them that deal with time. So that kind of eliminates our first and second one. So our last equation, that's going to be the one that we'll have to use. So because we're moving in the x direction horizontally, right, that's why we have these x subscripts there. When I recalculate the problem, not super necessary because we're only dealing in one dimension. So I'm going to say that that final equation we want to choose is going to be v squared is equal to v initial squared plus 2 times acceleration times final position minus initial position. So now plugging in our values, we got 6.4 squared. It's going to be equal to 2.1 squared. It's going to get added to 2 times our acceleration of 0.25 multiplied by our unknown final position x minus our initial starting position of 0. So real quickly going through the algebra here, 6.4 squared is going to give us 40.96. 2.1 squared is going to give us 4.41. Again, x minus 0 is just x, but 2 times 0.25 is going to give us 0.5x. We'll subtract over our 4.41. That's going to give us 36.55. It's going to be equal to 0.5x. Final step is we'll divide both sides by 0.5. So we know that over this leg of motion, our sprinter is going to be running a distance of 73.1 meters.